So our second thing here is that we're going to go after potential energy. So if I write the word potential energy, I typically write PE. But symbolically, that's not the way we write potential energy. Symbolically, we write it with the U. And that is pretty universal. Potential energy is a much more challenging concept than kinetic energy. So we have to be careful with that language. So what we're going to find here is that anytime work is done that changes the position of an object within a system, this work does not disappear, but reappears as stored work. As stored work. Unfortunately, the mathematics and how to really show you how we get potential energy is beyond the scope of this course. So we're going to have to rely heavily on pictures to give you a sense of this thing here. So let's go look at this thing here. So it turns out that we're going to deal with two potential energies. So there are two types of potential energies that we will deal with. One is called a spring potential. And the second kind is called a gravitational potential. So the spring potential energy, we typically write with US, and the gravitational potential, we typically write with UG. So let's deal with the spring potential first, and then I'll have to define a couple of things here. So here we go. So the first potential that we'll deal with is the spring potential energy. Now, suppose we have a system where we have a block and a spring attached. So suppose we have a spring block system. So I imagine that I have a wall, and then I'm going to have my block. So imagine that I have a block here. And what I'm going to see here is that I have a spring that's attached to the wall like this. And now what I'm going to do here is that I'm going to apply a force on this block. So now I'm gonna focus on this spring here. And what I'm not on the spring, but on the block. And what I'm going to do here is that I'm going to apply an external force. Now, this external force is going to be my hand. So I'm going to say that the external force is my hand pushing inwards. So as I compress this guy, I could imagine that maybe I compress it to this distance here.
Yeah.
And what you're seeing here is that I have now moved this block, this distance from here to there. So now let's look at this. So the work done by my hand does positive work. And the reason why it does positive work is because we can see here that my external force is in this direction, and my displacement is also in that direction too. So now, question. What about the work of the spring? Doesn't the spring do work too? The answer is it does exactly the same work, but in the opposite direction. So in this situation, what the spring does is it applies a force in the opposite direction. So you could imagine here that now I have a spring force that does work in the opposite direction from Newton's third law. The force of my hand must be the same as the spring force, but opposite in direction. So when I'm looking at this thing, what you're seeing here is that I could then say that the work of my hand must then equal the work of the spring. But this time there's a negative sign here and there's a positive sign in my hand. So the question is, this work must change the energy of the system. So there must be a change in energy in the system. So that's what we're talking about when we say spring. So the negative work of the spring changes the energy of the system. So now let's look at this change in energy. So the first thing that we want to do here is that, so let's focus only on the spring work, because we know it has to be the same as the positive work of my hand. So now I have this negative work of the spring, and this has to change the energy of the spring system. So the question is, what about the change in kinetic energy? So the question that I'm asking here, does the kinetic energy change? Well, when you look at this thing, let's say that we start at rest. So if I look at my spring system here, let's say that I start here, and I'm going to say that this guy starts at some initial speed of 0, and then I go through the compression phase. And then I'm going to keep pushing this until I compress it. And when I get to here, I'm now going to hold it stationary. So what you're seeing here is that, does the kinetic energy change? The answer is no. It starts at 0, it ends at 0, so therefore the kinetic energy of the system is 0. But that work had to have gone somewhere. Work is stored energy. The only way we can store any energy is if we define a new type of energy. So what this is telling us is that we must define a new type of energy, since energy is stored work. Work does not disappear, it reappears as energy, right? Energy is stored work, so it can't disappear. So this is what potential energy is then. So potential energy is the stored work due to changes in position. Then we have to ask this another question. Where is this stored work located? I really want to say the word stored. Where is it stored? It's in the compression of the spring. So when I look at the spring, I could imagine that I have my block here. And so when I look at my spring is all spread out. So what does my work do here? What my work does is that when I compress the spring, I'm deforming the spring so that the rungs of the spring here are all compressed. We can see here is that this is where the stored work is located. Okay? That's where it's located at. And because it's located there, we then say that this is where the change in potential energy of the spring exists. So now we got to get to the details here. And what we're seeing here is that the work energy theorem then says that if I do negative work of the spring, this changes the potential energy of the system. Now we got to be careful about this because the language is really slippery here. This implies that this is a positive work. Even though there's positive work done, note that there's that minus sign. So we have to deal with that minus sign because that becomes very cumbersome. So let's go look at what we mean by that. And the way we do that is we look at the details of the spring force. So now let's look at the details of the spring force and work. So the spring force is given by Hooke's law. And Hooke was an adversary of Newton. These guys really did not like each other very much. And here's what we find. If I have a spring force, which I will write as F of S, this is equal to minus K delta X. So note that this is a variable force. The spring force is a variable force, which is the first non-constant force we've dealt with. So if you're dealing with the non-constant force here, by the way, the kinematic equations don't apply anymore. You can't use them. So it's actually a big deal. And what you're seeing here is that there's a couple of things here. So the first thing that you want to see here is that K is known as the spring constant. And the spring constant tells us about the strength of the spring. So in other words, if I have a strong spring, that implies that it's harder to compress, which then means that it has a larger K value. If I have a weak spring, then it's easier to compress, so therefore I have a smaller K value. Delta X here, delta X, what it tells us here is that this is the term that says this is the distance that the spring is compressed. Oops. And so what we want to do here is that we want to set up a picture to show you what do I mean by this. Now, the easiest thing to imagine here is that as an example of Hooke's law, let's talk about its let's not do this. Let's talk about its compression dependence. So imagine that I have a spring, and when I allow this spring to come right here, where this thing hangs at, this is called the equilibrium point. And the reason why it's called the equilibrium point, because you could imagine here that I have the force of gravity coming down, and at the same time, I have a spring force pulling up. And if this thing is stationary, then these two forces balance out. This is what they call the equilibrium point, and typically we define this point right here at x equal to 0. So the equilibrium point is at x equal to 0. Now, if I pull this spring down below this equilibrium point, what you're going to find here is that the change in distance, so the change in distance from here to here, from the center of mass, this is the change in distance right there from that equilibrium point. So when I look at this thing, I'm going to have a spring force. That spring force is going to be this big, and it's going to be equal. So if I make this the positive direction and I make that the negative direction, then the spring force is going to look something like that. Now look what happens. Now suppose that I now take this block and I stretch it even more so. I pull down on it even harder. So when I'm looking at my equilibrium point, you can see that this distance now is even larger here. I should have been color coding these guys like this. So here, if I have the exact same spring, I had to pull with a greater force because my displacement was so large. So therefore, the spring force is larger here. In other words, how much I stretch or compress the spring depends on the distance that I actually move.